Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. In the last video, I walked through the analysis and design of the common collector transistor circuit. I even put things together on the bench to test my design. If you missed that video, there's a link up in the corner for you here. In this video, I'm going to look at the common base transistor circuit. I will go through the analysis and design of a common base circuit and then go to the bench to see how we did. I will be using Kirchhoff's voltage law to do this analysis. If you're not sure what that is, I have a video on that subject. There's a link up in the corner for you. If you're not familiar with this, it would probably be a good idea to take a look at it. I will also be utilizing the basic analysis model that I introduced in my video on that very subject. I've put a link to that video for your convenience up in the corner, just in case you're not familiar with it. I have a very important additional note that you must absolutely remember when creating a transistor circuit that doesn't live by itself. Anything that is connected to the input or the output of a circuit become part of the circuit. They become either current sources or current sinks that can and will change the operation of the circuit. So you've got to pay attention to this. Now, if you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, let's dive into the common base circuit. Well, the purpose of this exercise is to set the operating point of the transistor within its linear active region. So, what does this circuit look like? Well, let's begin by talking about the characteristics of the common base circuit configuration. It has a low input impedance, a high output impedance. It provides no current gain. It does provide voltage gain, and it is a non-inverting amplifier. That is to say, when the input voltage goes up, the output voltage also goes up accordingly. So what does this circuit look like? To begin with, the input to a common base circuit is the emitter. The output is the collector. The base in this example is connected to ground. Now, with the common base configuration, we're going to need two power supplies, one positive and one negative. Each of these power supplies will be 12 volts. I will call the negative 12 volt power supply VEE and the positive 12 volt power supply VCC. Yes, this can be accomplished with one supply, but this gets more complicated than I want to address here. The base emitter junction needs to be forward biased, which means that the emitter has to be at a lower voltage than the base, and the base is at ground potential. We can do this by putting a resistor between the emitter and the negative power supply. We will call this resistor RE. The collector base junction has to be reverse biased, which means the collector has to be at a higher voltage than the base, and the base is at ground potential. Furthermore, we are shooting for the active or linear mode of operation. So we want the voltage at the collector to sit at half of the positive power supply voltage, or 6 volts. We will do this by putting a resistor between the collector and the positive power supply. We will call this resistor RC. Now, we need to know the DC current gain of our transistor. We're using a 2N3904, so we will take a look at the data sheet to get an idea of what value to choose. The data sheet tells us that at a collector current of 10 milliamps, the DC current gain can be anywhere from 100 to 300, so we're going to say that the DC current gain of our transistor is 200. Now, with a little help from the data sheet and picking a number out of the air, our desired collector quiescent current operating point is going to be 10 milliamps. This is IC. So what are we trying to do? Well, we're going to calculate the needed emitter resistor and the needed collector resistor such that we have a collector voltage of 6 volts with a collector current of 10 milliamps using a 2N3904 transistor, which has a DC current gain of 200. Now, on to the analysis. Well, we will begin with the collector circuit because, well, we know the most about this. Our goal is to calculate the value of the collector resistor. So we start with Ohm's law, which tells us that the value of the collector resistor, RC, is equal to the voltage across the collector resistor, VRC, divided by the current through the collector resistor, IRC. And so now we ask, well, what do we know? Well, we know that the current through the collector resistor, in this case, is the same as the collector current. And one of our design goals is to establish a collector current of 10 milliamps. But we don't know the voltage across the collector resistor. So how are we going to get at that? Well, we use Kirchhoff's voltage law, which states that the sum of the voltages around any closed loop must be equal to 0. Because the base is connected to ground, and our definition is that the output, which is the collector voltage, is supposed to be 6 volts, we can work through Kirchhoff's voltage equation in this way. We start at the negative side of the power supply, VCC. We move up in potential to the power supply rail. This is a positive change in voltage. We move down in potential as we move through the collector resistor, RC. This is a negative change in voltage. Now we move down in potential once again as we move from the collector to the base of the transistor. This too is a negative change in voltage. We have returned to the negative side of the power supply via the ground connection. Now, let's write the equation that describes this trip around the loop. We have the power supply voltage VCC minus the voltage across the collector resistor VRC minus the voltage across the collector base junction VCB equals 0. So what do we know? Well, we know that the power supply voltage, VCC, is equal to 12 volts. We know that the voltage across the collector base junction is 6 volts because the target voltage of the collector is 6 volts and the base is at ground potential. Let's substitute these values in our Kirchhoff's voltage equation and we get 12 volts minus the voltage across the collector resistor, VRC, minus 6 volts equals 0. Now we're interested in the value of VRC, so we add VRC to both sides. Now we have VRC is equal to 12 volts minus 6 volts. Doing this simple math, we now know that VRC is 6 volts. Now we go back to our Ohm's law equation. We know that the voltage across the collector resistor, VRC, is 6 volts. And we know the current through it, IRC, is 10 milliamps. Putting these values into our Ohm's law equation gives us the value of the collector resistor is equal to 6 volts divided by 10 milliamps, which gives us a collector resistor value of 600 ohms. We have accomplished our first goal, calculating the value of the collector resistor. Now we can turn our attention to calculating the emitter resistor. As we work to determine the value of the emitter resistor, we start once again with Ohm's law, which tells us that the value of the emitter resistor is equal to the voltage across the emitter resistor divided by the current through it. So at this point, we don't know either the voltage or the current. So let's start our analysis by determining what the voltage across it is. To do this, we get to write Kirchhoff's voltage equation again, starting at the base of the transistor. And you ask, why start at the base of the transistor instead of the ground side of the power supply like we've done every other time? And that's a good question. Actually, I could do it either way. Both directions will work, but the math is simpler to demonstrate this way. There are fewer mathematical machinations to do. Okay, so starting at the base, which is at ground potential, and moving toward the emitter through the base emitter junction is a drop in voltage. This is a negative change in voltage. Then we continue to move to yet a lower potential through the emitter resistor. This is another negative change in voltage. Now we come to the negative side of the power supply, and moving toward ground, this is a positive change in voltage. Now let's write the equation which describes this trip around the loop. We have minus the voltage across the base emitter junction V sub BE, minus the voltage across the emitter resistor V sub RE, plus the power supply voltage V sub EE equals 0. So what do we know at this point? Well, we know the power supply voltage VEE is 12 volts, and we know that the voltage across the base emitter junction VBE is 0.7 volts per our model. Putting these into our equation, we have minus 0.7 volts minus V sub RE, the voltage across the emitter resistor, plus 12 volts equals 0. Well, we want V sub RE all by itself on one side of the equal sign, so we add VRE to both sides. This gives us the voltage across the emitter resistor is equal to minus 0.7 volts plus 12 volts. We do the simple math and we find that the voltage across the emitter resistor is 11.3 volts. With the voltage across the emitter resistor in hand, we can pursue the current through the emitter resistor. So what do we know? We know the collector current is 10 milliamps. We also know that the emitter current is related to the collector current with this equation. The emitter current is equal to the collector current times the quantity 1 plus beta on the top over beta, where beta is the DC current gain of the transistor. And we know the DC current gain beta is 200 for our 2N3904. And in this case, we also know that the current through the emitter resistor is the same as the emitter current. Well, knowing all these things, we get the current through the emitter resistor is equal to 10 milliamps times 1 plus 200 divided by 200. This yields a current of 10.05 milliamps. Now that we have this in hand, we can return to our Ohm's law equation. So what do we know? Well, we know that the voltage across the emitter resistor, V sub RE, is 11.3 volts. And we know the current through the emitter resistor, I sub RE, is 10.05 milliamps. Putting these into our equation, we get that the emitter resistor value is equal to 11.3 volts divided by 10.05 milliamps, which gives us an emitter resistor value of 1,124 ohms. So we've accomplished our second goal, to calculate the value of the emitter resistor. Now we get to go to the bench and see how this works in real life. To begin the process of putting this on the bench, I randomly chose a 2N3904 transistor from my collection. And then, looking in my junk box, I find my 604 ohm resistor to use for the 600 ohm collector resistor. I measured its actual value as 606 ohms. And the closest value I found for the 1.124 k ohm emitter resistor is a 1.21 k ohm resistor. I measured its actual value at 1.2042 k ohms. Well, these are not my actual calculated values. And if I'm going to really compare the bench results to the calculated results, I have to reverse engineer my circuit with these actual values. So let's begin with the emitter circuit, writing Kirchhoff's voltage equation using the same loop we used before, starting at the base of the transistor. What do we know? Well, we know that the power supply voltage, VEE, is 12 volts, and we know the voltage across the base emitter junction, VBE, is 0.7 volts. Putting this in our equation, we get minus 0.7 volts minus the voltage across the emitter resistor, V sub RE, plus 12 volts is equal to 0. Now, we're interested in calculating the voltage across the emitter resistor, VRE. So I will add VRE to both sides. We get the voltage across the emitter resistor is equal to minus 0.7 volts plus 12 volts. And this gives us the voltage across the emitter resistor is 11.3 volts. This hasn't changed with the difference in values of resistors. We need to calculate the current through the emitter resistor, I sub RE. To do this, I will turn to Ohm's law for help. It tells us that the current through the emitter resistor is equal to the voltage across it divided by the value of it. So what do we know? We know that the voltage across the emitter resistor, VRE, is 11.3 volts, and the value of the emitter resistor, RE, is 1.2042 k ohms. Substituting these values into our Ohm's law equation, we see that the current through the emitter resistor is equal to 11.3 volts divided by 1,204.2 ohms. This gives us the current through the emitter resistor of 9.38 milliamps. Now that we know the emitter current, we can turn our attention to the collector circuit. Well, the object of what we're doing here is to determine the voltage on the collector. To do this, we will begin with Kirchhoff's voltage equation that we previously used. So I ask, what do we know? Well, at this point, the only thing we know is that the power supply voltage, VCC, is 12 volts, and the voltage across the collector base junction is the same as the collector voltage because the base is connected to ground. But this leaves us with having to calculate the voltage across the collector resistor, V sub RC. We will begin with Ohm's law, which tells us that the voltage across the collector resistor is equal to the current through it times the value of it. The problem is the only thing we know at this point is the value of the collector resistor. So how do we determine the current through it? Well, we know that the collector current is related to the emitter current by this equation, which tells us that the collector current is equal to the emitter current times the quantity beta divided by 1 plus beta, where beta is the DC current gain of the transistor. So what do we know? We know that the emitter current, IE, is 9.38 milliamps by our previous calculation, and we know the DC current gain beta is 200 by our design assumptions. So substituting these values into this equation, we get the collector current is equal to 9.38 milliamps times 200 divided by 1 plus 200, which gives us a collector current of 9.34 milliamps. Now that we know this, we can go back to our Ohm's law equation. What do we know? We know that the current through the collector resistor is 9.34 milliamps from our last calculation, and we know the value of our collector resistor is 606 ohms, well, because we measured it. Putting these values into our Ohm's law equation, we get the voltage across the collector resistor is equal to 9.34 milliamps times 606 ohms, which gives us a voltage of 5.66 volts. Now we get to go back one more step where we started with the Kirchhoff's voltage law equation to finally calculate the collector voltage. What do we know? We know the power supply voltage, VCC, is 12 volts, and the voltage across the collector resistor, VRC, is 5.66 volts. Substituting these values in our equation, we get 12 volts minus 5.66 volts minus the voltage across the collector base junction, VCB, is equal to 0. Now we're interested in the voltage across the collector emitter junction, VCB, so I will add it to both sides to get it all by itself on one side of the equation. We get VCB, the voltage between the collector and the base, is equal to 12 volts minus 5.66 volts. Doing a little simple math, this gives us a collector voltage of 6.34 volts. Now, let's go to the bench and see how this comes out. So here's my setup, and here is the voltage at the output, which is the collector. Now, we expected 6.34 volts, and we got 6.33 volts. Now, that's cool. The question is, what happens if we put various randomly chosen transistors in place of the one that we have here? The first one gives us 6.36 volts. The second one measures at 6.34 volts. We get 6.33 volts with the third. And finally, I see 6.34 volts with the fourth. Notice that the quiescent operating point of the common base circuit didn't change very much. The good news is that this configuration is by nature very stable with regards to changes in the DC current gain of the transistor. This is because the common base configuration does not provide any current gain and is thus not affected by changes in the DC current gain of the transistor. So I suppose we should add one more characteristic for this configuration. Its DC operating point is not dependent on the DC current gain of the transistor. So there you have the common base configuration of the bipolar junction transistor. The plan for the next video is to demonstrate how to make the common emitter and the common collector configurations much more impervious to changes in the DC current gain of the transistors. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, Toodle-Oots.